The instructions detail how to build a voltage regulator circuit. Firstly, connect the bulb bone between the filament's terminals. This bulb is a 6.3 volts, 0.75 amps type 7377 filament bulb. It functions as both a ballast and a current limiter. Secondly, install the relay. Ensure its coil is connected between the coil terminals. Connect one set of the relay's contacts between the common and closed terminals. This is a double pole double throw, or DP/DT relay with a 5 volts, 50 ohms coil designed for printed circuit board or PCB mounting. Thirdly, connect the Zener diodes, D3 and D4, in parallel across the relay coil. These are 18 volts, 1/2 watt Zener diodes. Fourthly, connect the potentiometer, R5, between the POT terminals. This is a 100,000 ohms, 1/2 watt linear potentiometer. Fifthly, install the light emitting diode, or LED, which are LED1 and LED2, between the LED terminals. This is a bicolor red and green LED in the same housing. Sixthly, connect the test switch, SW2, between the test terminals. This is a single pole single throw, or SPSD, momentary on-off miniature push button switch. This circuit functions as a voltage regulator. The filament bulb serves as a ballast, limiting current flow. The Zener diode regulates the voltage across the relay coil, ensuring consistent relay activation. The potentiometer enables voltage adjustment for relay triggering. The LED indicates the relay state, with red signifying a triggered relay and green indicating a released relay. The test switch facilitates manual relay triggering. The relay is designed to switch an external load. This circuit is beneficial in applications requiring precise voltage for relay activation. The filament bulb can be exchanged to accommodate diverse current requirements. Let's elaborate on each component and its role in the circuit. The filament bulb, beyond providing illumination, is essential as a ballast resistor. A ballast resistor is a resistor used to limit current in a circuit. Incandescent bulbs have a positive temperature coefficient. This means that as the temperature of the filament increases, its resistance also increases. This characteristic is used to help regulate the current. When the voltage across the circuit increases, the current through the bulb also increases. This increase in current causes the filament to heat up, which in turn increases its resistance. This increase in resistance limits the current, preventing it from rising too high. The specified bulb is rated at 6.3 volts and 0.75 amps. This means that it's designed to operate at 6.3 volts while drawing 0.75 amps of current. This value is essential for proper circuit operation. The relay serves as an electrically controlled switch. Relays are electromechanical devices that use an electromagnetic coil to control a set of contacts. When current flows through the coil, it generates a magnetic field that attracts a metallic arm, moving the contacts. A DP/DT relay has 2 poles and 2 throws. This means it can control 2 separate circuits, and each circuit has 2 possible connections. A common terminal is the common connection for each pole. A closed terminal is the normally closed connection. When the relay is not energized, the common terminal is connected to the closed terminal. When the relay is energized, the common terminal is disconnected from the closed terminal and connected to the open terminal, if the relay is 1. The relay coil has a resistance of 50 ohms and requires 5 volts to operate. It's critical to ensure that the power supplied to the coil meets these requirements to prevent damage. Zener diodes are a special type of diode that allows current to flow in the reverse direction when a certain voltage is reached. This voltage is called the Zener voltage. In this circuit, the Zener diodes are used to regulate the voltage across the relay coil. They are connected in parallel with the relay coil. This means that they share the same voltage. When the voltage across the relay coil exceeds the Zener voltage of the diodes start to conduct current in the reverse direction. This limits the voltage across the relay coil, preventing it from rising too high. The specified Zener diodes have a Zener voltage of 18 volts and a power rating of 1/2 watt. The power rating indicates the maximum amount of power that the diode can dissipate without being damaged. It's crucial to select Zener diodes with appropriate voltage and power ratings to ensure proper circuit operation and prevent failure. A potentiometer is a variable resistor, allowing you to manually adjust the resistance in a circuit. It typically consists of a resistive element with a sliding contact that moves along the element. The position of the sliding contact determines the amount of resistance between the terminals. In this circuit, the potentiometer is used to adjust the voltage at which the relay is triggered. By adjusting the potentiometer, you can change the voltage divider ratio, which in turn changes the voltage applied to the relay coil. A 100,000 ohms linear potentiometer indicates that the resistance changes linearly with the position of the potentiometer's knob or slider. The LED provides visual indication of the relay status. A bicolor LED contains two LED in a single package, typically red and green. By controlling the current through each LED, you can produce different colors or combinations of colors. In this circuit, the red LED indicates that the relay is triggered, while the green LED indicates that the relay is released. This provides a simple and effective way to monitor the relay's operation. The test switch is a momentary push-button switch that allows you to manually trigger the relay. When the button is pressed, the switch closes, completing the circuit and energizing the relay coil. This allows you to test the circuit and verify that the relay is functioning properly. An SBSD switch has one pole and one throw. This means that it can only control one circuit and it only has one connection. In this circuit, the test switch is connected in series with the power supply and the relay coil. When the switch is closed, it completes the circuit and allows current to flow through the relay coil. Now, let's discuss how to assemble the circuit. Firstly, connect the filament bulb bone between the filament's terminals. This connection is crucial, as the bulb will act as a current limiter. Ensure the bulb is securely connected to prevent loose connections. Secondly, install the relay. The relay coil should be connected between the coil terminals. Also, one set of contacts should be connected between the common and closed terminals. The correct orientation of the relay is important to make sure the connections are accurate. Refer to the relay's datasheet for the correct pinout. Thirdly, connect the Zener diodes, D3 and D4, in parallel across the relay coil. Ensure that the polarity of the diodes is correct. The cathode of the Zener diode is typically marked with a band. The Zener diodes will protect the relay coil from overvoltage. Fourthly, connect the potentiometer R5 between the POT terminals. The potentiometer allows you to adjust the voltage at which the relay triggers. Secure the potentiometer to the terminals properly. Fifthly, install the LED between the LED terminals. Ensure that the polarity of the LED is correct. The longer lead of the LED is typically the anode, and the shorter lead is the cathode. Sixthly, connect the test switch, SW2, between the test terminals. The test switch allows you to manually trigger the relay. After assembling the circuit, test it to ensure that it is functioning properly. To test the circuit, apply power to the circuit. Adjust the potentiometer to the desired voltage level. Press the test switch to manually trigger the relay. Observe the LED to confirm that it is indicating the correct relay status. Now, let's talk about the troubleshooting. If the circuit does not function properly, troubleshoot it. Firstly, check all the connections to ensure that they are secure. Secondly, verify that all the components are functioning properly. Thirdly, check the voltage levels at various points in the circuit to identify any problems. The filament bulb may burn out over time. If the bulb burns out, replace it with a new bulb of the same type and rating. The relay may fail to trigger. If the relay fails to trigger, check the voltage across the relay coil. If the voltage is too low, adjust the potentiometer or check the power supply. The Zener diodes may fail. If the Zener diodes fail, replace them with new diodes of the same type and rating. The potentiometer may become damaged or worn. If the potentiometer becomes damaged or worn, replace it with a new potentiometer of the same type and rating. The LED may burn out. If the LED burns out, replace it with a new LED of the same type and color. The test switch may fail. If the test switch fails, replace it with a new switch of the same type. Consider the power supply requirements. The circuit requires a power supply that can provide the necessary voltage and current. The voltage should be stable and free of noise. The current should be sufficient to power the relay coil and the LED. Consider the safety precautions. When working with electrical circuits, follow safety precautions. Avoid touching exposed wires or components when the circuit is powered on. Use a multimeter to measure voltage and current. Wear appropriate safety gear, such as safety glasses. Now let's consider some applications for the circuit. This circuit can be used in applications where precise voltage is required to trigger a relay. For example, it can be used in an overvoltage protection circuit. In an overvoltage protection circuit, the relay is used to disconnect the load from the power supply when the voltage exceeds a certain level. This can protect the load from damage. It can also be used in an undervoltage protection circuit. In an undervoltage protection circuit, the relay is used to disconnect the load from the power supply when the voltage falls below a certain level. This can prevent the load from malfunctioning. The circuit can be used in a battery charger. In a battery charger, the relay is used to control the charging current. When the battery is fully charged, the relay disconnects the charging current. This prevents the battery from being overcharged. It can be used in a temperature controller. In a temperature controller, the relay is used to control a heating or cooling element. When the temperature reaches a certain level, the relay turns off the heating or cooling element. This maintains the temperature at a constant level. It can also be used in a light controller. In a light controller, the relay is used to control the brightness of a light. When the light level reaches a certain level, the relay turns off the light. This saves energy. Finally, let's discuss some modifications to this circuit. The filament bulb can be replaced with a different type or resistance if necessary to meet the specific current requirements of the circuit. For example, a resistor can be used in place of the filament bulb. If a resistor is used, the resistance should be chosen to limit the current to the desired level. The Zener diodes can be replaced with different Zener diodes with different Zener voltages. This allows you to adjust the voltage at which the relay is triggered. The potentiometer can be replaced with a different potentiometer with a different resistance. This allows you to adjust the range of voltage adjustment. The LED can be replaced with a different LED with a different color. This allows you to customize the visual indication of the relay's status. The test switch can be replaced with a different switch with a different type. This allows you to customize the manual triggering of the relay. Firstly, ensure proper heat dissipation for the filament bulb, especially if using a higher wattage bulb to prevent overheating and potential fire hazards. Secondly, select a relay with appropriate contact ratings considering the voltage and current requirements of the external load it will switch to avoid contact welding or failure. Thirdly, consider using a heatsink for the Zener diodes if they dissipate significant power to prevent overheating and ensure stable voltage regulation. Fourthly, implement a reverse polarity protection circuit, such as a diode in series with the power supply, to prevent damage to the circuit components in case of accidental reverse polarity connection. Fifthly, use a properly rated fuse in series with the power supply to protect the circuit from overcurrent conditions and potential damage. Sixthly, ensure that all wiring connections are secure and properly insulated to prevent short circuits and electrical hazards. Seventhly, consider using a shielded enclosure for the circuit to minimize electromagnetic interference and improve overall circuit performance. Eighthly, implement a snubber circuit, such as a resistor-capacitor network across the relay contacts to suppress voltage transients and reduce contact arcing, extending the relay's lifespan. Ninthly, consider adding a hysteresis circuit to the relay trigger to prevent oscillations or chattering around the switching threshold, ensuring stable and reliable operation. Tenthly, design the circuit layout with proper grounding techniques to minimize noise and ensure stable operation, especially in sensitive applications. By understanding the function of each component, assembling the circuit correctly, testing it thoroughly, and following safety precautions, one can create a reliable and effective voltage regulator circuit for many applications.